April 9, 1963. The morning was cold and overcast. At Pier 11, the nuclear submarine USS Thresher, SSN 593, sat low in the water. Tugs were already maneuvering to assist the vessel away from the berth. This was not a combat patrol. It was a post-overhaul test dive. The submarine had spent 9 months in dry dock for repairs and upgrades. Now, the Navy required a series of sea trials to certify the ship was ready to return to active duty. The schedule was tight. The submarine force was expanding rapidly to meet the Soviet threat, and Thresher was the most advanced attack submarine in the American arsenal. She needed to be at sea. On board were 129 men. The complement included 96 enlisted sailors and 16 officers. In addition to the military crew, there were 17 civilians. These were technical experts from the Portsmouth Naval Shipyard, the Naval Ordnance Laboratory, and contractors like Sperry Gyroscope. Their presence was standard for sea trials. They were there to monitor the new equipment, check for vibrations, and observe the deep dive tests. Among them was Lieutenant Commander John Wesley Harvey, the commanding officer. Harvey was a capable and experienced nuclear submariner. He had served on the USS Nautilus during its historic transit under the North Pole. He had taken command of Thresher in January, overseeing the final stages of the overhaul. This was his first major sea trial with the ship. At 8 hours, the lines were cast off. The Thresher moved slowly down the Piscataqua River, heading for the open Atlantic. The plan was straightforward. They would proceed to a designated test area east of Cape Cod. During the transit, they would conduct shallow dives and equipment checks. The following morning, April 10th, they would rendezvous with the submarine rescue ship USS Skylark. Then they would conduct a deep dive test, descending to the submarine's maximum test depth of 2,300 feet. To understand the disaster that followed, it is necessary to understand the machine itself. The USS Thresher was the lead ship of a new class of nuclear attack submarines. Launched in 1960, she represented a radical shift in naval architecture. Previous nuclear submarines, like the Nautilus or Skate, were essentially surface ship hulls adapted for underwater propulsion. The Thresher was designed from the keel up for the deep ocean. Her hull was a teardrop shape, optimized for underwater speed and silence. The most significant innovation was the steel. The hull was constructed from HY80 steel. This was a high-yield alloy capable of withstanding 80,000 pounds per square inch of pressure before yielding. This material allowed Thresher to operate at significantly greater depths than her predecessors. While the exact test depth was classified at the time, it was known to be approximately 1,300 feet. Operating at this depth gave the Thresher a tactical advantage. She could hide in thermal layers of the ocean that sonar could not penetrate. She could outrun and outdive Soviet torpedoes. She was the apex predator of the Cold War. However, this increased depth capability introduced new engineering challenges. The pressure at 1,300 feet is approximately 580 pounds per square inch, psi. The hull compresses under this load. Every opening in the hull, valves, periscopes, propeller shafts, becomes a potential failure point. The internal piping systems, which carry seawater for cooling the reactor and auxiliary machinery, are subjected to this same immense pressure. On the Thresher, these saltwater systems were extensive. They snaked through the engine room and the auxiliary machinery spaces, carrying the ocean inside the ship. The construction of these piping systems relied on a joining technique called silver brazing. Unlike welding, which melts the base metals to fuse them together, brazing uses a filler metal melted between two close-fitting parts. It is similar to soldering, but performed at much higher temperatures, above 800 degrees Fahrenheit. The Navy chose silver brazing for submarines because it was effective for non-ferrous pipes, like copper-nickel, and was generally faster and cheaper than welding every joint. There was a critical flaw in this decision. Silver brazing requires legitimate craftsmanship and rigorous quality control. If the joint is not heated evenly, or if the surfaces are not perfectly clean, the silver filler will not bond correctly. It might create a void inside the joint, an air pocket where no metal connects the two pipes. Visually, from the outside, the joint might look perfect, but internally, it could be weak. During the Thresher's construction, non-destructive testing (NDT) methods like ultrasonic inspection were in their infancy for this specific application. The primary method of inspection was a hammer test, literally striking the joint with a hammer and listening to the ring, or a visual check. Thousands of silver brazed joints were installed in the Thresher's saltwater systems. Many of these joints were in difficult-to-reach areas, hidden behind equipment or lagging. In 1961, another submarine, the USS Barbel, experienced a near-catastrophic failure of a silver brazed joint during a dive. The joint failed, spraying high-pressure water onto the electrical panels. The crew barely managed to surface. This incident alarmed the Bureau of Ships. They ordered a review of silver brazed joints on all new submarines, including Thresher. When Thresher entered the Portsmouth Naval Shipyard in July 1962 for her post-shakedown availability, PSA, the inspection of these joints was a priority. The results were concerning. Ultrasonic testing was performed on a sample of the joints. The inspectors found a failure rate of approximately 14%. If this rate was extrapolated to the thousands of joints on the ship, it meant Thresher could have hundreds of substandard connections in her high-pressure seawater systems. The shipyard faced a dilemma. To repair every potential bad joint would require stripping the submarine down to its frame. It would take months, perhaps a year. The Navy needed the Thresher back in the fleet. A compromise was reached. The shipyard would repair the joints that were easily accessible and those that showed the most obvious signs of defects. They would pressure test the systems to 150% of the maximum operating pressure. If the joints held during the hydrostatic test, they were deemed safe. The assumption was that a static pressure test in the harbor was equivalent to the dynamic stresses of the deep ocean. This assumption ignored the reality of hull compression. At 1,300 feet, the submarine's hull shrinks by several inches. The rigid piping inside does not shrink. This differential movement places immense strain on the pipe joints, strain that a static harbor test does not simulate. Work on the Thresher continued through the winter of 1962 and the spring of 1963. It was a period of intense activity. The shipyard workforce was pushed hard. Overtime was common. The logbooks from this period show a frantic pace to clear the job orders before the April deadline. There were issues beyond the piping. The main ballast tank blow system, the emergency system used to force water out of the ballast tanks and surface the ship, was also scrutinized. The system relied on high-pressure air stored in flasks. To surface rapidly, this air would be blasted into the ballast tanks through narrow valves. The rapid expansion of air causes a drastic drop in temperature, the Joule-Thomson effect. If the air contains moisture, this temperature drop can cause ice to form. Ice can clog the strainers in the valves, blocking the airflow. Without airflow, the water cannot be expelled. The submarine cannot surface. The Navy was aware of this theoretical risk. Dryers were installed to remove moisture from the air banks. However, the efficiency of these dryers under rapid cycling conditions was not fully verified on the Thresher. On the evening of April 9th, Thresher was moving into deeper water. The mood aboard was professional, but tired. Sea trials are exhausting. The crew runs drills constantly. They test the sonar, the propulsion, the trim systems. As night fell, the submarine reached the edge of the continental shelf. Below them, the ocean floor dropped away into the abyss. They rendezvoused with the USS Skylark, ASR-20, the next morning. Skylark was a Penguin-class submarine rescue ship, a converted tug from World War II. It was not a modern vessel. It lacked advanced underwater tracking gear. Its role was to maintain surface communications with Thresher via an underwater telephone, UQC, and to act as a safety reference point. If Thresher got into trouble, Skylark had a rescue chamber, but it could only be used if the submarine was sitting on the bottom at a survivable depth. In 8,400 feet of water, the depth at the test site, there could be no rescue. If the hull failed, the physics of the ocean would resolve the situation instantly. At 07:47 on April 10th, Commander Harvey ordered the start of the deep dive test. The Thresher began her descent. The plan was to descend in increments, leveling off at various depths to check for leaks and monitor the hull's integrity. 0 or 100 feet, all clear, 300 feet, all clear, 400 feet. The crew checked for leaks. Officers walked the ship, inspecting sea valves and the engine room. 650 feet. Halfway to test depth, the descent was slow, controlled. Commander Harvey was communicating with Skylark via the UQC. The voice quality of the underwater telephone is often poor, distorted by the water density and thermal layers. It sounds like a voice coming through a long metallic tunnel. At 8:35, Thresher reached roughly 1,000 feet. The pressure on the hull was now over 440 psi. The steel was compressing. The pipes were groaning under the strain. Down in the engine room, the main seawater circulation pumps were running, pushing cold ocean water through the condensers to cool the steam plant. This system was the lifeline of the propulsion. It was also the system with the highest number of silver brazed joints. At 8:53, Thresher signaled that she was approaching test depth, 1,300 feet. This was the limit. This was where the engineering margins were tested. At this depth, the pressure is 580 psi. The ocean is pushing against every square inch of the hull with the force of a sledgehammer. At 9:02, Thresher transmitted a course change. The transmission was routine. The ship was at test depth. Speed was slow. The reactor was operating normally. Then, silence. On the surface, the crew of the Skylark waited. The minutes ticked by. The underwater telephone remained quiet. The sonar operators listened to the background noise of the ocean, the shrimp, the waves, the mechanical hum of their own ship. They expected a status update. At 09:13, a transmission cut through the static. It was garbled. The voice was Harvey's, but the tone was different. The Skylark's logbook recorded the partial message: "Have positive up angle, attempting to blow." This was not a routine report. Positive up angle meant the ship was pitched up, trying to climb. Attempting to blow meant they were using the emergency ballast tank blow system. They were in trouble. They were trying to get to the surface immediately. The Skylark operator grabbed the microphone. "Are you in control? Repeat, are you in control?" Silence. Then, seconds later, another transmission. It was heavily distorted, almost unintelligible. Witnesses on the Skylark later testified they heard the words 900, or possibly test depth. And then, the final words, cut off by a distinct, low-frequency sound. The sound was described by experienced sonar men as air rushing into a tank. But then came a second sound, a dull, heavy thud. It was not an explosion in the chemical sense. It was the sound of a structure failing. It was the sound of the ocean reclaiming the space that had been carved out by the steel. The Skylark called again and again. "Geranium, this is Angus. Reply." Geranium was Thresher's call sign. Angus was Skylark. There was no reply. The Atlantic Ocean at that location is 8,400 feet deep. The pressure at the bottom is 3,800 psi. Nothing biological or mechanical designed for the surface can survive there without protection. The Skylark circled the area, looking for a periscope, a flare, an oil slick. They saw nothing but the gray waves of the North Atlantic. The most advanced ship in the U.S. Navy had simply vanished. To reconstruct the final minutes of the USS Thresher, we must rely on acoustic data, the physics of submarine design, and the later findings of the Naval Court of Inquiry. There are no survivors to tell the story. However, by analyzing the specific distress calls and the timeline of the sounds recorded by the Skylark and distant SOSUS listening stations, a horrifyingly clear picture emerges. The catastrophe likely began at approximately 09:09 a.m. The Thresher was at test depth, moving slowly, likely around 3 to 5 knots. This low speed is critical. A submarine relies on two forces to change depth: buoyancy and hydrodynamic lift. At high speeds, the hull acts like an airplane wing. Angling the dive planes upward generates lift, driving the ship to the surface even if it is heavy. But at 3 knots, the planes generate almost no lift. The submarine is entirely dependent on buoyancy. If it gets heavy, it sinks. Somewhere in the engine room, a silver brazed joint failed. It was likely a pipe ranging from 2 to 5 inches in diameter, part of the saltwater auxiliary cooling loop. At 1,300 feet, water doesn't leak, it cuts. A failure of a 2-inch pipe at that depth allows water to enter the ship with the velocity of a bullet. The spray would have been deafening, a jet of water stripping insulation off cables, shorting out electrical panels, and filling the compartment with a blinding, freezing mist. The immediate threat wasn't drowning. It was the electrical grid. The spray hit the main electrical switchboards for the reactor coolant pumps. These pumps are the heart of the nuclear propulsion system. They circulate the water that keeps the reactor core from melting down and transfers heat to the steam generators. When the water hit the bus bars, the breakers tripped to protect the system. The reactor SCRAM mechanisms triggered instantly. Control rods slammed into the core. The fission reaction stopped. This is a safety feature. In a reactor accident, you want the core to shut down, but in a deep dive flooding casualty, a reactor SCRAM is a death sentence. When the reactor trips, the steam supply to the main turbines is cut off. The propeller stops turning. The Thresher lost propulsion. She was now a 3,700-ton steel tube, taking on water, drifting at 2,300 feet, with no forward momentum to generate lift. In the control room, Commander Harvey would have seen the indicators flash red. Reactor SCRAM. Main engine stop. Flooding in engine room lower level. The ship would have begun to feel heavy. The stern, filling with water, would start to drag the ship down. Harvey was a trained nuclear engineer. He knew the procedure. He had seconds to act. He ordered emergency blow. This is the ultimate lifeline. The chief of the watch would have actuated the toggles for the main ballast tank blow system. High-pressure air, stored at 4,500 psi in banks of flasks, should have rushed into the ballast tanks, displacing the water and making the ship buoyant again. It should have been a violent, roaring ascent to safety, but down in the piping of the blow system, physics betrayed them. As the air rushed through the valves at supersonic speed, it expanded rapidly. The adiabatic cooling effect dropped the temperature of the air instantly. The moisture in the air, moisture that the dryers had failed to remove, froze. Within seconds, ice formed on the strainers, filters, inside the valves. The ice grew rapidly, choking the flow. The roar of the air turned into a wheeze, then silence. The ballast tanks remained full of water. The Thresher did not get lighter. She got heavier. Without propulsion and without buoyancy, the Thresher entered a terminal descent. She began to sink below her test depth. 300 feet, 1,400 feet, 1,500 feet. The hull was now groaning under stresses it was never designed to take. The HY-80 steel was yielding by compressing plastically. Inside the ship, the crew would have been fighting for their lives. The auxiliary diesel engine could not be started instantly at that depth. The battery drive, a backup electric motor, was likely engaged, but it was too weak to overcome the weight of the flooding water. The ship was sliding backward and downward, the positive up angle. Harvey reported being a desperate attempt to point the bow at the surface, even as the ship sank stern first. At 09:13, Harvey made his final, garbled transmission. He likely knew in that moment that the ship was lost. The hull was compressing faster than the ocean. The bulkheads were buckling. The sounds heard by the Skylark, the cracking, the popping, were the internal structures failing. At approximately 2,400 feet, the calculated collapse depth of the hull, the physics of the ocean delivered the final blow. The pressure was now over 1,000 psi. The hull could no longer resist. It didn't leak slowly. It buckled instantaneously. This is called an implosion. It is difficult to comprehend the speed of a deep-sea implosion. It happens faster than the human brain can process nerve impulses. The collapse of the Thresher's pressure hull would have taken approximately 0.1 seconds, 100 milliseconds. The human brain requires about 150 milliseconds to register pain or visual stimuli. The walls of the submarine moved inward at supersonic speed, roughly 2,000 miles per hour. The air inside the ship was compressed instantly. When air is compressed that quickly, it heats up. The temperature inside the Thresher would have spiked to several thousand degrees Fahrenheit in a fraction of a second. It was essentially a diesel engine cycle on a massive scale. Compression, heat, ignition. The hull didn't just crush, it shredded. The steel shattered like glass. The interior of the ship was instantly incinerated and pulverized. The men aboard did not drown. They did not suffocate. They ceased to exist before their brains could even register that the hull had failed. One moment they were alive. A tenth of a second later, they were part of the physics event. The energy released by the collapse was equivalent to the detonation of a large bomb. This energy wave traveled through the ocean, recorded by SOSUS hydrophones hundreds of miles away. It was a singular, violent acoustic signature that marked the end of 129 lives. Following the implosion, the debris rain began. Thousands of pieces of the Thresher, shredded steel, insulation, plastic, personal effects, began the long, slow drift down to the ocean floor at 8,400 feet. The heavy machinery, the reactor compartment, the engine components, fell straight down. The lighter debris drifted in the current, creating a debris field spread over thousands of square yards. On the surface, the Skylark continued to call. They threw hand grenades into the water, a standard signal to a submarine to surface immediately. They waited. They saw an oil slick appear, a thin sheen of diesel and hydraulic fluid rising from the deep. Then came pieces of cork insulation. Then, a pair of yellow rubber gloves. By the afternoon of April 10th, the Navy began to accept the reality. The Chief of Naval Operations went to the White House to inform President Kennedy. The news broke to the world. The U.S. Navy had lost its first nuclear submarine. The invincibility of the nuclear fleet was a myth. The search operation that followed was unprecedented. The Navy directed the oceanographic research ship Atlantis the Set and the bathyscaphe Trieste to the site. It took months to locate the wreckage. When they finally found it, the images were sobering. The Thresher was not a ship anymore. It was a junk pile. The largest identifiable section was the tail cone, sitting upright on the bottom. The rudder still turned, a silent tombstone. The rest of the ship had been shredded into scrap metal. The photos from the bottom confirmed the violence of the event. Twisted piping, crumpled plating, a sonar dome smashed flat. But the most chilling discovery was what they didn't find. The hull sections were effectively turned inside out. This confirmed the implosion theory. The ocean had not just entered the ship, it had passed through it. The loss of the Thresher was not just a tragedy, it was a wake-up call that shook the foundations of the U.S. Navy. The investigation that followed, the Naval Court of Inquiry, would be one of the most exhaustive in maritime history. It would expose a culture of complacency, where good enough was accepted in place of perfect. It would reveal that the shipyard was overwhelmed, that the inspectors were underqualified, and that the warning signs, like the failures on the USS Barbel, had been systematically minimized in the rush to build a fleet. But before the reforms could begin, the Navy had to answer a terrified public and the grieving families. Why was a ship deemed safe on April 9th, destroyed by the ocean on April 10th? The answer lay not in enemy action, but in the mundane, invisible details of brazing flux, pipe wall thickness, and the freezing point of water in a valve. The Thresher was killed by the accumulation of small errors, each one survivable on its own, but fatal when combined at 400 psi. The ocean does not give up its secrets willingly, and in April 1963, the technology required to locate a submarine at a depth of 8,400 feet was experimental at best. The Navy launched a massive recovery effort, designated Task Group 89.7, which turned the patch of Atlantic Ocean off Cape Cod into a grid of desperate activity. Surface ships crisscrossed the area towing magnetometers and Geiger counters, searching for magnetic anomalies or radiation spikes that would indicate the resting place of the nuclear reactor. For weeks, they found nothing but the natural magnetic noise of the seafloor and the frustration of equipment failures. It wasn't until June that the bathyscaphe Trieste was brought to the scene. The Trieste was not a submarine in the military sense. It was a deep submergence vehicle, a fragile sphere of high-strength steel suspended beneath a massive float filled with aviation gasoline. It was the only machine in the world capable of reaching the bottom and returning. Its pilot, Lieutenant Don Keach, descended into the abyss, a journey that took hours through absolute darkness. When his external lights finally illuminated the seafloor, he did not find the intact hull of a submarine. He found a field of industrial confetti. Keach reported seeing millions of pieces scattered across the silt. He identified a shoe, a clock stopped at the moment of destruction, a manual, and vast quantities of twisted metal that looked as though it had been passed through a shredder. The condition of the wreckage provided the first definitive forensic evidence of the disaster's mechanics. If the Thresher had flooded and sunk intact, the hull would have remained largely whole, crushed perhaps, but recognizable. The severe fragmentation confirmed the violence of the event, a high-velocity implosion that had pulverized the steel, turning the ship inside out in a fraction of a second. While the Trieste documented the physical remains, a different kind of search was underway at the Portsmouth Naval Shipyard. A Naval Court of Inquiry had been convened to determine the cause of the loss, presided over by Vice Admiral Bernard Austin. This was not a standard debriefing. It was an autopsy of the entire naval industrial complex. The court called 120 witnesses and reviewed 1,300 documents, and as the testimony unfolded, the image of the Thresher as the pinnacle of engineering began to disintegrate. The investigation quickly zeroed in on the thousands of silver brazed joints in the saltwater piping systems. The court summoned the shipyard's chief metallurgists and quality control officers, demanding to see the inspection records. The data was damning. The inquiry revealed that of the 145 silver brazed joints that had been inspected by ultrasonic testing during the Thresher's overhaul, 14% were found to be defective. When pressed by the Admiral on the implications of this failure rate, the shipyard representatives were forced to admit a terrifying statistical reality. If 14% of the tested joints were bad, it was statistically certain that hundreds of the thousands of untested joints were also defective. The shipyard's defense was that the systems had passed the hydrostatic pressure tests in the harbor. The court brought in independent engineers to dismantle this argument. They explained that a pipe joint might hold water at 1.5 times operating pressure when the hull is static and the environment is controlled. However, at 1,300 feet, the submarine's hull compresses significantly, shrinking by inches. The rigid piping inside does not shrink. This differential movement places immense shear and bending forces on the joints, stresses that a static harbor test simply cannot simulate. The Safe ship was, in reality, a lattice of potential failure points, waiting for the crushing force of the deep ocean to expose them. But the most chilling evidence presented to the court did not come from the Thresher itself, but from her sister ship, the USS Thresher, SSN 606. The Thresher was nearly identical to the Thresher and was nearing completion. In a desperate attempt to understand why the emergency blow system had failed to save the crew, the Navy ordered a live test on the Thresher. They moored the submarine at the dock and simulated the conditions of a blow from test depth pressures. Engineers filled the air banks with high-pressure air and opened the valves to flush the ballast tanks. The result was immediate silence. The air roared for a few seconds and then stopped completely. When technicians disassembled the valves, they found the strainers, fine mesh filters designed to protect the valves from particulate matter, were completely clogged with ice. The rapid expansion of the high-pressure air had caused the temperature to plummet, freezing the moisture in the air instantly. The dryers installed to remove this moisture were undersized and ineffective for the volume of air being moved. The design of the strainers created a perfect trap for ice crystals. This test proved that the Thresher's emergency system was flawed in its fundamental thermodynamics. Even if the crew had executed the procedure perfectly, the physics of the system were working against them. It was a fail-deadly design, providing a false sense of security that evaporated the moment it was needed most. The inquiry also exposed a deep cultural divide within the Navy, highlighted by the testimony of Admiral Hyman G. Rickover, the father of the nuclear navy. Rickover, known for his abrasive and exacting standards, testified that the failure likely did not originate in the nuclear propulsion plant, which was built to rigorous, standardized codes. He pointed the finger at the conventional side of the Navy, the shipbuilders and bureaucrats who applied antiquated construction methods to modern deep-diving vessels. He criticized the lack of standardization, noting that there was no central authority responsible for the safety of the submarine's hull integrity in the same way he was responsible for the reactor. A welder could be certified one day and do poor work the next with no oversight. Materials were often substituted without documentation. The concept of a unified safety standard for the non-nuclear components simply did not exist. The final report of the Court of Inquiry was a massive indictment of the Navy's acquisition process. Its conclusion was clear. The most probable cause of the loss was a failure of a saltwater piping system joint, which led to flooding in the engine room. The resulting spray shorted out electrical circuits, causing a reactor SCRAM and loss of propulsion. The crew attempted to blow ballast, but the system froze due to inadequate dryers and poor valve design. Heavy and powerless, the Thresher exceeded her collapse depth and imploded. The Navy's response to these findings was not merely to fix the remaining ships of the Thresher class, it was to tear down the entire philosophy of submarine construction and rebuild it from the keel up. This marked the birth of the submarine safety program, known as Subsafe. Arguably the most rigorous quality assurance program in industrial history, Subsafe was built on the ruthless premise that the ocean is trying to destroy the vessel every second it is underwater. The program introduced the concept of objective quality evidence, OQE. It was no longer sufficient for a worker or a foreman to verbally confirm that a valve had been repaired. There had to be a verifiable paper trail: who performed the work, what specific materials were used, the batch number of the steel, the torque settings applied, and the identity of the inspector. If the paper trail was missing or incomplete, the component was assumed to be defective and was removed. The implementation of Subsafe froze the American submarine fleet. Every submarine was restricted in depth, unable to return to their test depths until they had been retrofitted and certified under the new standards. For the new construction projects, this meant delays of months or years. The use of silver brazing for high-pressure seawater systems was effectively banned in favor of welding, which offered greater strength and allowed for X-ray inspection. The ballast blow system was redesigned completely. The narrow strainers were removed. The air dryers were upgraded to industrial capabilities, and the capacity of the air banks was increased to ensure the ship could surface even with a flooded compartment. The tragedy of the Thresher cost 129 lives, but the Subsafe program born from the debris field has likely saved thousands since. The rigorous paranoia that defines modern American submarining, the obsession with logs, the endless drills, the fanaticism about watertight integrity, is the direct legacy of those final minutes in April 1963. Since the program's inception, the United States Navy has not lost a single Subsafe-certified submarine to a non-combat accident. The disaster transformed the culture of the Navy from one that prioritized speed and schedule to one that prioritized technical perfection, acknowledging that in the deep ocean, the margin for error is zero. The effectiveness of the Subsafe program was tragically underscored 5 years later by the loss of another submarine, the USS Scorpion, SSN 589. In May 1968, the Scorpion disappeared in the Atlantic southwest of the Azores with 99 men aboard. While the exact cause of the Scorpion's loss remains a subject of debate, theories range from a battery explosion to a hot-running torpedo. One fact is indisputable: the Scorpion was not Subsafe certified. Due to budget constraints and operational demands during the height of the Cold War, the Navy had deferred the full Subsafe retrofits for the Scorpion. She was operating with a reduced safety margin, a decision that proved fatal. The loss of the Scorpion cemented the Navy's resolve that there could be no middle ground. Following 1968, the regulations were tightened further. No submarine would ever again be permitted to deploy without the full, uncompromised seal of Subsafe certification. The result is a statistical anomaly in the history of industrial safety. Since the implementation of the program, the U.S. Navy has lost 0 Subsafe certified submarines. The Thresher was the sacrifice that purchased this record. The wreckage of the Thresher eventually became the subject of one of the most famous cover stories in oceanographic history. In 1985, Dr. Robert Ballard approached the Navy with a proposal to test a new deep-sea camera sled called Argo. He wanted to use it to find the RMS Titanic. The Navy agreed to fund the expedition, but with a strict classified condition. They were not interested in the luxury liner. They were interested in the nuclear reactors of the Thresher and the Scorpion. The Cold War was still active, and the Navy needed to know if the reactors were leaking radiation into the environment or if the Soviets had visited the sites. Ballard's mission was to survey the 2 sunken submarines first. Only if he finished that job on time could he use the remaining sea days to hunt for the Titanic. Ballard's survey of the Thresher site provided a grim, high-definition update to the grainy photos taken by the Trieste 2 decades earlier. The Argo sled flew over the debris field, mapping the distribution of the wreckage. The imagery confirmed that the nuclear fuel was secure. The reactor compartment had held together well enough to contain the core, despite the violence of the implosion. The environmental monitoring revealed that there was no significant radiation leakage. The ocean, in its vastness, had diluted the trace elements to negligible levels. The mission was a success, and Ballard used the technique he learned searching for the Thresher, following the trail of light debris to find the heavy main mass, to locate the Titanic days later. The world celebrated the discovery of the liner, unaware that the technology and the funding had come from the grave of the Thresher. The psychological impact of the disaster reverberates through the submarine force to this day. The memory of the event is institutionalized in the training pipeline. Every prospective commanding officer, before taking command of a submarine, must travel to Washington, D.C. to meet with the Director of Naval Nuclear Propulsion. It is a grueling, technically demanding interview process that has not changed significantly since Admiral Rickover started it. The shadow of the Thresher hangs over these meetings. The candidates are grilled on their understanding of systems, of backup procedures, and of the moral weight of their responsibility. They are reminded that their competence is the only thing standing between their crew and the crushing pressure of the deep. There is no room for the good enough attitude that pervaded the Portsmouth Naval Shipyard in 1963. For the families of the lost men, the legacy is less abstract. It is defined by the empty chairs at dinner tables and the generational trauma of a loss without closure. In 2019, after decades of secrecy, a retired naval officer brought a lawsuit forcing the Navy to declassify the remaining documents from the Court of Inquiry. The release of these pages provided the families with the final, painful details of the administrative failures that led to the accident. It confirmed what many had long suspected. The Thresher did not die because of a mysterious force of nature or enemy action. She died because of a schedule. She died because the pressure to field a new weapon system outpaced the ability to verify its safety. The tragedy of the USS Thresher serves as a permanent case study in the ethics of engineering. It demonstrates that in high-risk environments, safety is not a layer that can be added on top of a finished product. It must be woven into the molecular structure of the organization. The 129 men who died on April 10, 1963, were the victims of a system that forgot to respect the physics of its own domain. They were crushed by the ocean, but the failure began on the drafting tables and in the inspection logs long before the ship ever left the pier. Today, at the Portsmouth Naval Shipyard, works continues on the latest generation of Virginia-class attack submarines. The technology has advanced beyond anything Commander Harvey could have imagined, but the fundamental rules remain unchanged. The pressure at test depth is still 580 pounds per square inch. The freezing point of water is still 32 degrees, and the ocean is still waiting for a mistake. In a quiet corner of the shipyard, there is a memorial. It lists the names of the civilians and sailors who were lost. It is a place of reflection, but also a warning. It reminds every welder, every electrician, and every admiral that the rules of Subsafe are not written in ink. They are written in blood. Subscribe to Maritime Tales, because the sea has a memory, and it keeps its dead.